Hey everyone, welcome back to our channel ALGOBRAIN AI. Today, we'll be diving into one of the most fascinating breakthroughs in computer vision, and that is Meta's Segment Anything model. Imagine a tool that can instantly outline and identify an object in an image with incredible precision and flexibility. That's exactly what SAM model does, and today I'm gonna break down how it works. Before we jump into SAM, let's understand the problem that it solves. So suppose I am training a model for traffic analysis. In order to achieve that, I have to annotate 10,000 images with cars in it. Now, traditionally, what you do is work with each image and either draw a bounding box around the car or a polygon or a mask around the car. Suppose if this process takes 30 seconds of your time, we can imagine how much time it will take to annotate 10,000 images. This is where SAM model comes in. It can easily segment the image and you can easily annotate the images using the SAM model. Oh. The segment anything model is developed by researchers at Meta, and the key points for it are it is incredibly versatile. It can segment almost any kind of image. It is highly interactive. In fact, users can also try this model on the official site. And it is zero shot capable. So, in order to identify an object, it does not need to be trained on that specific object. It can work as a zero shot model wherein your object can be detected even if that object is not trained on the base model. Now, let's look at the architecture of the segment anything model. So, in segment anything model, there are three main parts to the model. First is image encoder. Second is prompt decoder. And third is mask decoder. So, for SAM model, an image is inputted and it goes through the image encoder, which transforms the image into an numeric representation, that is image embeddings, and it does so using NAE, which stands for Masked Auto Encoder. Let's look at how the Masked Auto Encoder works. Give the Masked Auto Encoder an image of dimensions 5 cross 5. It will mask 75% of the image Nexo, and then it passes to an encoder which converts the unmasked pixels of the image to a numeric representation. Then the masked pixels of the image are added to the embeddings like so. Ye- Wherein n equals 25, and then using the decoder, the model tries to predict this masked values based on the encodings of the unmasked pixel values. So using the decoder, the masked autoencoder tries to achieve the input image by predicting the masked values. Now that the image is encoded into a numerical representation, that is image embeddings, it goes through a bitwise AND operation between a specified mask object and a numeric representation of image embeddings. So for suppose in the original image, I mask out this region. So that is converted into a numeric representation. There is the mask, and the bitwise AND operation is performed between the mask and the embeddings, which in turn lets the model know that we have to perform the segmentation process within this masked area only. Now the second part of the image is the prompt decoder. So prompt decoder takes points as an input. It takes bounding boxes as an input, and it takes text as an input. You can even segment the images using prompts in segment anything model. So for points, it takes coordinates of points and whether the point is positive or negative. So in an image, you specify which points belong to positive and which points belong to negative. That way, the model understands to include these points and to not include these points. In bounding boxes, it takes the coordinates of the 4 points as input. And in text, it takes prompt, which in turn is encoded for the segmentation purposes. Now, the third main part of the segmenting model is the mask decoder, which takes image embeddings and encoded prompts as input. and outputs 3 masks with scores. So let's understand how the Mask Decoder works. So in Mask Decoder, first, all the prompt token embeddings are represented in a 2D matrix form, and the 3 output embeddings are added to the prompt embeddings. So here, 3 output embeddings are added to the prompt embeddings. After that, in the token to image attention, all the prompt embeddings are updated with the contextual information from the image embeddings. Similarly, in image to token attention, all the image embeddings are updated with the contextual information from the prompt embeddings. The output of this module is prompt aware image embeddings which goes through convolutional translation twice. What this does is it upsamples the image embeddings. Now, the output of this module would be a prompt aware image embeddings which goes through convolutional translation 2 times in order to upsample the embeddings. Okay. After that, from the prompt embeddings, we extract the 3 output masks and we send it through an MLP module in order to map each of them to 256 dimensional features. Here, the dimensions of the prompt embeddings is 256 features x64, x64, which goes through upsampling. So the final dimensions would be 256 times 512 times 512. Okay. Now we take a dot product of the upsampled embeddings and the mask embeddings in order to generate the masks. Also, we train a separate MLP layer here to generate IOU scores. So the output of the model would be 3 masks with their IOU scores. So as we discussed before, what happens is we provide an image input to the model. It encodes the image to form image embeddings. Here we may or we may not specify the mask embeddings, which specifies how much of an area of an image we would like to work on. So then we use the prompt encoder to encode our points or box or text inputs. Then we use the image embeddings along with the prompt encoded prompts and we put it in Mask Decoder and it outputs 3 masks with their scores. Now that we know the architecture of the SAM model, let's understand how the SAM model is used in real life with a code implementation. So first, in order to implement the SAM model, we have to install some prerequisites. So currently, since I'm working on Lightning AI, I'm gonna be installing OpenCV, Torch, and G segment anything model. After installing OpenCV and Torch, we have to install the segment anything module from the GitHub, that is Facebook research slash segment anything. So from there, we have to install segment anything using this pip command. We also need to download the weights for the SAM model, and the weights for the model are available on the GitHub repository itself. Here are the weights. Wit underscore h is the largest model, wit underscore l is the medium sized model, and wit underscore b is the smallest model. We'll download wit underscore h model using the wget. Once this is done running, the SAM underscore with underscore h pth file will be saved on our directory. Now we need to import all the necessary libraries. Once this is done, I'm gonna load a sample image. Now that all the libraries are imported, I'll import a standard image of a traffic. So I hope you'll be knowing a little bit of basics about how OpenCV works and why I used the color underscore BGR to RGB. After this, I'll initialize a figure. Then I'll show the image. Now that I've loaded the image, I'll plot the image using the matplotlib.pyplot. So I'll initialize a figure of xi equals 10 now, 10 by 10. Then I'll do plt.im show. So this is how the original image is. This is the image of the traffic that we'll be working on. As you can see, there are a lot of cars, there are a lot of rickshaws, there is a green bus, there are red cars, which we'll try to segment using the segmenting model. Now that I've plotted this image, I'll load the SAM model by specifying the SAM model checkpoints as the relative path the download and model. Then I'll specify what the model type is. In this case, we are using the wet underscore h model. I'll also specify the device, which is CUDA. So After that, I'll initialized SAM, which is SAM model registry. And then we initialized the predictor. This is equals to SAM predictor model. Let's see if this code runs without any errors. Once we initialize the predictor, we set the image for the predictor using the set image, and we use our original image for it. Now for point estimate, now for mask estimation using points, I'll be defining 6 points. This is 1, 2, 3, 4, 5, 6. 6 points. You can use a front end in order to map the points on the given image. So for suppose this point equates to a certain function, certain value on the x and y axis. So using this scale, I have mapped 6 points as input points. Then I'll initialize the labels for the points, which will be a list of 6 points, wherein 1 represents points in the foreground and 0 represents points in the background. I'll make an np.array this list, and then I'll get mask points, score points, and logits from predictor, wherein point coords equals to input points. Point labels equals to input labels. And we'll do multi-mark output equals true. Doing so will get mask points, which is of length 3. We also get the scores for it, which is of course of length 3, because the SAM model outputs 3 masks. Now this points equate to this car. So based on this car, I selected 1, 2, 3 points as foreground and 3 random points as background for selecting this car. So now I'll initialize the figure of fixed size 10 by 10. Masked So here, as you can see, we selected 3 points as foreground and 3 points as background. That way, the SAM model was able to mask this following car. Now we'll do segmentation of this rickshaw using bounding boxes. Now, of course, you can use a GUI to find the bounding boxes around the rickshaw. I'll be initializing 4 points, which equates to bounding boxes around the rickshaw. This equates to points x1, y1, x2, y2. Now, using the same logic, we use mask box. We calculate the masks within the box and scores within the box and logits using the predictor.predict. Now that we have the masks and the scores for the bounding box, we'll display the results using elter.figure. So as you can see here, we have defined the bounding boxes around the rickshaw area, and the SAM model was easily able to identify the rickshaw from the traffic using bounding boxes. Now, segmentation using text prompts can be achieved using clip model. So in the next video, we'll understand how the clip model works, what its architecture is, and how we can use clip model to segment the objects using text prompts. For more projects like this, make sure to subscribe to our YouTube channel ALGOBRAIN AI and make sure to comment down which projects you'd like for us to implement next. Thank you.